connecting to YouTube now. And we're live.
Yeah, we've got about 59 people so far. Hello, everybody. We've still got people joining bit by bit, but I'll go ahead and start things off by introducing this seminar. This is Denise Kabusta at University College Cork in Ireland. I'm delighted to welcome you here today on behalf of the organizing committee to this latest in a series of seminars focusing on high resolution radio astronomy, the sharpest view of the radio universe, VLBI connecting astronomers worldwide. I want to mention just a few logistics of the webinar before we begin. You will be muted throughout the presentation, but you're invited to type in any questions you may have for our speaker through the question and answer facility. You can send in questions both during and after the presentation, but questions will be answered only after the presentation. Please try to write your questions clearly and keep them short. We'll aim to get to as many of your questions as we can, and we apologize in advance if your question is not among those that we have time to answer. I'd now like to introduce our speaker. Michael Johnson is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, a lecturer in the Harvard Department of Astronomy, and an inaugural member of the Harvard Black Hole Initiative. Michael got his PhD from the University of California, Santa Barbara. And he co-led the Event Horizon Telescope imaging team that produced the first image of a black hole, which I think we're all familiar with. And he's a member of the Event Horizon Telescope Science Council. His research focuses on studying galactic and extragalactic black holes and pulsars through imaging with extremely fine resolution. His contributions across the Event Horizon Telescope project include developing new imaging methods to produce movies of rapidly evolving black holes and studies of magnetic fields near black holes using polarimetry. Today, he is going to tell us about shadows and photon rings, imaging supermassive black holes with the Event Horizon Telescope. Over to you, Michael.
Great. Thank you so much, Denise, for the kind introduction. And can I just quickly confirm that you see my screen? Perfect.
Yes, that's fine.
Great. Well, the Event Horizon Telescope is a project that's been in development for decades. And of course, our major result was released 2 years ago when we showed the first images of a black hole. But more is still coming. We actually just last week released updates to that result, the first polarized images. So today I'd like to tell you a bit of the story of the EHT, a bit of the background behind the results last week, and what you might expect from the future. So this story is really all about M87. So M87 is a giant elliptical galaxy tucked between the constellations of Virgo and Leo. So this is an enormous galaxy, but it's also about 55 million light years away. And what that means is that even with the best optical telescopes we have, like the Hubble Space Telescope, all we can really see is this ball of stars with a faint jet extending away from it. Now, of course, with very long baseline interferometry, we can peer deeper into this system. And as we look at higher and higher frequencies with VLBI, the jet becomes more and more translucent. So we can peer deeper and deeper to its heart till we get to 230 gigahertz. And this is the first image of a black hole ever taken, released by the Event Horizon Telescope in 2019. So what we think we're seeing in this image is hot plasma heated to something like 100 billion degrees. That's very close to the event horizon of a black hole. And so that plasma is glowing bright in synchrotron radiation, but the black hole casts a shadow on it because light that comes too close to it will be trapped by the black hole, and light that's emerging too close to the black hole is also heavily redshifted. So the easiest thing to read off this image is just how big this black hole is. It sets the size of the whole system. And so we estimate that it's something like 6.5 billion times the mass of the sun. So that's absolutely gargantuan by any measure. It's one of the biggest black holes in the universe, inferred by any technique. And so it's really an incredible scale to ponder. But the other incredible scale is just how small this is on the sky. So it's also, it's 55 million light years away. So this has about the same angular size as a donut sitting on the moon or an atom held at arm's length. And this is why VLBI is really imperative to be able to reach these scales and make images of these incredibly small objects. Now, I was asked to give the seminar and told not to expect that everyone's a VLBI expert. So I just want to give you a bit of background on how VLBI works. And for that, it's helpful to draw some inspiration from ducks. So here are some ducks. They jump into a pond, and they start kicking their feet furiously. So they're kicking away, and they're stirring up the water. It's turbulent and irregular near the ducks. But if you look further away, you see these nice outward propagating wave fronts that are very coherent. So again, you look close to where those ducks are, and you see the water stirred up and turbulent and irregular. And then far away, you have these nice coherent outward propagating wave fronts. Okay, so the toy problem that I'd like you to imagine is, suppose that you're standing on the boundary of the pond, and your job is to tell me where the ducks are. But the hiccup is that we'll say that you're blindfolded, you can't see where the ducks are, and that you also can't hear them. So all you can do is you can wade into the pond just a little bit, and you can feel the sloshing pattern of the water against your feet. And so your job is to tell me where the ducks are just by feeling that sloshing pattern of water against your feet. Okay, so let's unpack this a little bit, and we'll use an even simpler example. So here's our toy problem. On the left, we have some ducks in a pond where the ducks are close together, and on the right, we have the ducks spread a little further apart. So let's start with the case on the left. We'll let those ducks start splashing. They start kicking their feet. The water stirred up and turbulent, and then further away, you see it emerge into these outward coherent wave fronts. And if you just imagine that you're on the boundary there, you see that sloshing pattern up and down against your feet. Okay, now let's move to the right. So these ducks are a little further apart. Same game. We'll let them start kicking their feet. They stir up the water. It's stirred up and turbulent and irregular close to them, and further away, it's more coherent. And on the boundary, again, you see that sloshing of the water up and down. So how would you be able to tell where the ducks are? There's really two quantities of interest here. The first is the amplitude of the sloshing pattern. And it turns out that that's the same in these two cases. So if you're standing there and you're just feeling the water sloshing against your feet, you actually can't tell me where the ducks are. However, there's a second property of the system, and that's the coherence length around the pond. So let's imagine that you're at this pond with a friend, and they're standing near you. And the question is, if you compare the sloshing pattern that you feel with that of your friend, are you seeing roughly the same pattern, or are you seeing different patterns? And in the case on the left, it turns out your friend could move far away on the pond and you'd still see about the same pattern. Whereas on the right, your friend has to be pretty close to you, or they'll start to see a different pattern. So this amplitude only tells us how many ducks there are and how strongly they're splashing. But this coherence length that you and your friend can measure is what really encodes the information of where the ducks are the pond. Now, this is a rather whimsical example, but it turns out to have a close parallel with VLBI. So in VLBI, we're not observing ducks, of course, but we are observing electrons. And these electrons aren't splashing in a pond, but they're gyrating around magnetic fields. And as they do so, they're sending out ripples of electromagnetic waves. Now, we're not putting telescopes around this pond, but we can spread them as far as possible around the Earth, and we can record those electromagnetic waves. And then we can look at the correlations between each pair of telescope after the fact, and that encodes the image of the source. And it turns out to have this beautiful mathematical correspondence where every baseline, every pair of telescopes samples a single spatial frequency of the source. So if the image on the sky were a song, each pair of telescopes would be hearing just one note of that song. And if you want to piece together the whole image or hear the whole song, what you need is many different baselines at different orientations and different lengths. And you can then piece all that information together to get the image. Okay, so pulling all this together, this is the Event Horizon Telescope. It's a worldwide VLBI network, and it uses telescopes that were pre-existing. What we did in the EHT was to add equipment so that these sites could work together as a VLBI array. And this typically involved installing an atomic clock at every site so that they could be perfectly synchronized, and installing high-speed recording equipment because we have to swallow huge amounts of bandwidth in order to achieve the required sensitivity. So what's amazing is that in 2017, when we produced this image, we were only observing MED7 with 5 different locations on the Earth. So we only had 10 baselines. So we're really in this regime where every data point is precious. And a lot of the analysis that we do is directly on these interferometric visibilities, these Fourier measurements of the image. We can go all the way to an image. We have sort of just enough information to do that. But we're really still kind of scraping the surface. It's not like something like the EVN where you have many sites and you can form images directly and have a lot of confidence in that. So the EHT is still rapidly expanding. And because we're in this data-starved regime, each extension can really open up entirely new capabilities. So in 2017, we observed with 8 stations at 6 different geographic sites, and we observed with 32 gigabits per second recording. In 2018, so this data is unpublished still, we actually added a new station in Greenland, and we doubled the recording rate. And in addition to that, we also went to dual sideband recording. So we're swallowing instantaneous swaths of bandwidths that are much wider. And this is very important for things like polarization studies. And in 2020, we had a very exciting campaign planned. We were adding a new site in Arizona at the Kitt Peak Telescope, and we were also adding a new site in France, the Noema Array. But unfortunately, these observations were canceled because of COVID. But we really, through heroic efforts on the instrumentation side of the project, we have things up and running, and we'll be trying for a 2021 campaign with these new additions next week. So it's really moving forward at a breakneck pace. Now, why is imaging with the EHT so subtle? I mean, in this data-starved regime, it's a challenging problem, but there's really more to it than that. So just to give you a sense of this, we're trying to take a picture of something that's never been seen before. We're doing this with only a handful of measurements that are extremely difficult to calibrate, and we're doing this with an instrument that's never been used. So it's not just that this was the first image of a black hole made by the EHT, it's actually the first image of anything that the EHT ever produced. So in this really challenging climate, how can we possibly ensure that our results are reliable? And for this, we've developed a lot of machinery that's kind of unorthodox in standard VLBI, but that has been really central to us gaining confidence in our results. So the first thing that we did when the data were ready is that we started with blind imaging comparisons. So the moment that the data were ready to be imaged, we actually distributed it to 4 separate imaging teams, and then we ceased all contact between the teams. So we wanted each of these teams to be making their own decisions about the data, which data to flag, which data they thought were poorly calibrated, and so forth. We wanted each team to make their own decisions about how to use those data and also their own decisions about which imaging algorithms to use. We didn't want any groupthink or any sense that one particular team was making a really nice image that the other teams were trying to either explicitly or implicitly reproduce. So we sent out the data, and then we let these teams work furiously for 7 weeks in isolation. And at the end of 7 weeks, we came together at an imaging workshop to compare for the first time what the different teams had produced. So these were the images that were shown. And what I love about these images is, they do have a consistency. Each of them shows a ring. Each ring has a relatively deep depression, and each ring is brightest in the south. But beyond that, the images have striking differences. Some of them have hints of extended structure, like a jet. They have different azimuthal structure around the boundary of the ring, different knots and lobes, and so forth. And I think in a conventional VLBI analysis, you might be tempted to analyze these and try to make sense of what you were seeing with a single preferred pathway. Whereas here, we really we think that it's just exposing the limitations of working with such sparse data, and it's really just fundamental uncertainties in the data that we probably can't beat down much further. So this was a photo of the workshop. This is the first time that any of us had seen this combined results from all the teams. I think it was the moment in the project when we knew we had a result, when we knew that we were really seeing the shadow of a supermassive black hole. So it was really an exciting milestone. But of course, what's next from there? We have to converge on a final image, and you can't do this by just picking your favorite. So to move forward on that, we've also relied on a second thing, which is comparisons with synthetic data. So the beautiful thing about synthetic data is that there's a known ground truth image that generates the data. So what we do is we'll generate lots of different synthetic data sets from different images with different morphologies, not just rings and not just what we think a black hole might look like, but also things like disks and doubles and so forth to make sure that we're not overly tuning our algorithms to see what we want to see. So then we optimize all of our different algorithms but based on their performance on these synthetic data. And then we apply those optimized algorithms to the real M87 data. And so here is the final result using 3 different imaging pathways. DiffMap is standard VLBI software that uses the clean algorithm. EHT Imaging and Smiley are both new software packages that use a technique called regularized maximum likelihood. And these were both, the development of these was led by graduate students in each case. So it's been really fun in the project. There's been a huge amount of algorithmic work done, generally led by the junior scientists in the collaboration who have really done some wonderful work. And the other thing I want to emphasize is that all of our data products are available online. You can go to our website and download them, and also the imaging scripts. So these packages are open source, and so you can download them, reproduce the results. And if you have ideas for new algorithms, we're hoping that this will really be a test bed for developing more. Okay, so there's our images. We have them. Next question, of course, is what do they mean physically? How do these inform us about the M87 accretion and jet system? And as I mentioned, it's pretty easy to estimate the mass of the black hole from these images. It's related to the diameter of the ring that you see in the sky. However, beyond the mass, we actually found that it was quite difficult to derive physical constraints on the models. So up at the top are 3 different models from general relativistic magnetohydrodynamic simulations. The first 2 are models that we call sane, or standard and normal evolution. So these have relatively weak magnetic fields. And the third is a magnetically arrested disk, or MAD. And this has strong dynamically important magnetic fields. The image on the left is actually a rapidly spinning black hole, where it's actually a retrograde spin. So it's spinning the opposite direction of its accreting material. The one in the middle has no spin of the black hole at all. And the one on the right has a rapid spin that's prograde. And then there's also, pardon, this parameter R high, which is a phenomenological parameter that governs the electron thermodynamics and tells us how these images light up from the GRMHD fluid simulations. You can see these have different parameters on all three of these, but they're actually all consistent with the image on the sky that we see. So one of the things that was really striking for us was just how successful the simulations were in predicting the image that we would see on the sky. But the counterpoint there is that we actually had very weak constraints on the physics of the accretion system from our image. So the black hole spin, even the location of the emitting material, whether it's in the forward jet or the disk or the counterjet, how strong the magnetic fields were, those were all poorly constrained. And going to something that you might consider maybe the most fundamental parameter of the system beyond the black hole mass, the accretion rate, even that was very poorly constrained. And successful models had different accretion rates by something like 3 orders of magnitude. So how can we improve these? How can we tighten these constraints? And there, the natural answer is polarimetry. So these are the results that were released just last week. And that's the first polarization results from the Event Horizon Telescope on M87. So this is just showing our measurements in the visibility domain. So this is the native measurement domain. You see that M87 is actually very weakly polarized. It's only a few % polarization when it's unresolved. But on our long baselines, we see much higher polarization fractions. So this is really rich information, and it's a chance for us to make full polarization images that directly probe the magnetic field properties because synchrotron radiation is so highly polarized. So again, we followed a similar pathway in trying to develop confidence in our results. We started with groups converging for a workshop and using 3 different imaging algorithms to try to analyze these data. And these are doing both the polarization imaging and the polarization calibration at the same time because the calibration is such an imperative part of the final images. So these are 3 algorithms, again, EHT imaging, and then PolSolve is a package led by Yvonne Martí-Vidal, and LPCal is a more traditional package. And all 3 of these softwares produced similar results at this workshop. You can see on the center column there of figures, that's the polarization fraction across the image. And so you see that we see polarization predominantly in the southwest of the image. And on the right is the calibration terms, these instrumental D terms that describe polarimetric imperfections in the observing system. And those were also very consistent among all 3 methods. So this is an image from the polarimetry workshop, which happened in the summer of 2019. And of course, over the last almost 2 years, the hard work has been turning those into really robust publishable results. So the next stage after those preliminary comparisons were to use, again, comparisons with synthetic data to try to derive fiducial method averaged images using wide parameter surveys on lots of different image morphologies. So here's our final fiducial image on each day. Similar to total intensity, you see that adjacent pairs of days look very similar in morphology. April 5th and 6th look very similar. April 10th and 11th also look very similar. But there's pronounced evolution over just the single week of observing. We're actually seeing this source evolve before our eyes. So it's really an exciting opportunity for deeper studies. You know, this is not some dormant beast. We're looking at a continuous snapshot of. It's a living, breathing system that we can study in real time. Now, to be able to constrain models, what we did is we derived a series of image metrics that were as simple as possible so that we could assess which of the GRMHD simulations were compatible with the image metrics that we saw. So the first was the net image fractional polarization. So this is the polarization that's unresolved by the EHT. There's then coherent cancellation across the image. And we found that this was between 1 and 3.7% across all the reconstructed images using all the different techniques. So a fairly narrow range of possibilities there. That tells us that the overall image either has to be very unpolarized or it has to have precisely canceling polarization structure across the image. The next metric that we used was the image average linear polarization fraction. So this is looking at the resolved images and just saying what's the typical polarization fraction we see once you have the resolution of the EHT, which is about 5M. And we found that has to be higher, of course, because there isn't coherent cancellation across the whole image. And we found that it's 5.7 to 10.7%. So it's still rather low. The intrinsic synchrotron polarization fraction would be something like 70%. So there's still something that's canceling out a lot of polarization structure, even at the resolution of the EHT. Now, the third metric we used, which turns out to be the most constraining, is the amplitude and phase of the rotationally symmetric azimuthal mode. So this is a metric that was derived actually by 3 graduate students in the EHT, Daniel Palumbo, George Wong, and Ben Prather. And what they realized is if you take the ring image, you can decompose it into a set of Fourier modes. And these are indexed by the azimuthal mode number, M. And there's one mode in particular that turns out to be very powerful at constraining the different models, and that's this beta 2 mode. So those 4 images on the right, you see this the beta 2 mode, whether it's 1, -1, I, or -I. That'll tell you whether it's a radial structure, a toroidal structure, or whether it's a twisting structure that's either right or left-handed. And so when we tried that on all the reconstructed images, we found that the amplitude of this beta 2 mode was between 0.04 and 0.07, and that the argument to the beta 2 mode was constrained to a fairly narrow range. And that turns out to be extremely constraining for these GRMHD models. So when we look back at those constraints from before, we can see how polarization tightens them up. So this is just showing the accretion rate on the left and the jet power on the right. And you see that our accretion rate that before was acceptable over something like 3 orders of magnitude now really tightens up to something like a factor of 5 uncertainty. So you really see the power of polarization in constraining these models. In addition to that, all of the passing models, all the models that are consistent with the EHT measurements, are these magnetically arrested disks. So it's telling us that, at least for the models that we're currently considering, it seems to need fairly strong magnetic fields near the black hole to be consistent with the data that we see. And these have magnetic fields of something between 1 and 30 Gauss when weighted by the emission. Now, we've seen that the polarization that's resolved by the EHT is still rather low, 10 or 20% at most. And so there has to be something that's depolarizing the radiation from the synchrotron limit. And we think that what's doing that is actually intrinsic Faraday depolarization. And we're finding that can actually be a very, very strong effect on these numerical simulations. And we're also seeing that across all our data products, from total intensity to polarization to Faraday rotation and circular polarization, time variability is absolutely key. We see significant evolution over only a single week. And then, of course, it's going to be very exciting to compare the M87 images and data across years of different EHT campaigns. So one other thing you might be wondering is, when we looked at that zoom in of M87, every VLBI experiment ever done on M87 in the past has been dominated by this booming jet. And then we get to the EHT and you see this donut with no hint of a jet at all. How is that possible? Why is that not some huge red flag for our imaging? And the answer is the EHT doesn't have enough short baselines. So basically, the EHT has all these large baselines that resolve out the jet, and they focus on the horizon scale structure. And if we had more short baselines, then we'd be able to achieve we'd be able to probe the spatial scales where we think the jet emission is dominant. And the other aspect of this is that in VLBI, people are, at least when studying these systems, you're used to looking at things on log scales because the jets have such suppressed brightness. They really only show up in that way. But the EHT data, or EHT images, because we have so few baselines, we only have a dynamic range of about 10. So we're showing linear scale images, and we think that if we push the dynamic range, we'd be able to see the jet directly in these images. So here's an example. This is the jet in M87 at 7 millimeters using this wonderful data taken over a long campaign by Craig Walker. And what's exciting is that they actually recorded data over many different epochs that were closely spaced. So you can stitch these together and make a movie of the source. And here again, we see that the jet in M87 is alive, it's writhing. You can see this continual outflow, hints of a spine sheath structure, and all sorts of interesting information there. And so if we could achieve higher dynamic range with the EHT, then we can understand how all of this exciting dynamics is linked to the black hole. We think that magnetic fields that thread the horizon are actually dragged as a black hole rotates, and they could be providing the source of power for the jet. So a central goal for us is to be able to connect all of this exciting dynamics all the way down to the horizon. And to do that, we have to continue developing our array. So we're working on developing something called a next generation event horizon telescope. So this would be a significantly enhanced EHT ground array with something like 10 new sites, 8 times wider bandwidth. It would include 345 gigahertz, so 50% sharper resolution. And we might be able to include even new data paradigms so that instead of taking years to produce results, we can do them in closer to real time. And we think that with this array, even with small sites, perhaps even small as 6 meters, distributed around the world, we should be able to increase our dynamic range by a factor of 100, which would give us enough sensitivity to detect this full jet launching region and connect it to the horizon. And also, this increased coverage gives us enough measurements that we can do snapshot imaging of Sagittarius star. We would have the chance to really do full movie reconstructions during flares and understand what's driving the dynamics. So this is all related to kind of large scale structure in a system like M87. The other question is, how much sharper can the resolution be? And there we're learning a lot of exciting new things. And this is really related to what the image of a black hole really looks like. So here, I think to understand these new ideas, we can draw some inspiration from Charles Darwin. Not Darwin the naturalist, but actually his grandson, who was a physicist. And so Darwin was considering this problem of, what would the image of a star look like if a star was near a black hole? And of course, you'll see one image of the star that's just distorted on the sky and stretched a little bit. And that's because the black hole bends light from the star. But Darwin realized that you would also see additional images. So he wrote, each star, in addition to its direct image, will show a series of faint ghosts on both sides of the black hole. There will be a ghost on its left side, just outside 3√3m. Furthermore, there will be secondary ghosts on both sides, still closer to 3√3m, which come from rays that have gone a complete circle around the black hole before escaping to the telescope. The successive ghosts of a sequence crowd together more and more closely to such an extent as exactly to counterbalance their increasing feebleness. He then added, this result seems to have no practical importance at all. And what's extraordinary is he was right about everything except that last sentence. So to understand this, we think that behind this blurry donut that we've seen with the EHT, if we could see with perfect resolution, we would see a bright photon ring. So this is a simulated image of a black hole. And this photon ring is actually a stack of subrings. And these subrings are indexed by the number of times that a photon went around the black hole, just like in that Darwin picture. And because of this, the subrings also are self-similar. And they're self-similar with a fractal relationship that's determined solely by the properties of the black hole spacetime. So just to give you a quick example of this, here's an animation. There at the center, you see this black hole, and here are some rays that are passing close to it, but not so close that they get trapped. So the rays come in, they pass close, they get bent, and then they arrive on a distant observer screen, and that provides this n=0 image. But there will also be some photons that went a half loop around the black hole before coming to us. And it turns out that because of the properties of the lensing and demagnification, these photons will pile up on the much sharper ring that we call the n=1 ring. Then, of course, there will be some photons that go a whole loop around the black hole before coming to us. And these are going to pile up on the still sharper feature that we call the n=2 ring. And so the final image that we see is the aggregate of all of these different subrings. It's the stack of all of them, all these photons combining together to produce this image of the black hole. So this is just a property of the lensing from the black hole, and it also has some really deep mathematical properties. So one is that the properties that we see around the boundary of the ring are actually related to a property in radius near the black hole. So it's sort of a holographic mapping where the small emission radii actually contribute to the material on the bottom of this image, and the large emission radii contribute to the emission on the top of the image. So this gives us a way to decompose the space-time just by looking at properties of the image. Now, in addition to that, it turns out that subrings, while they're negligible on images, you could barely see them on this very high resolution image that I have up because they become faint so quickly. But it turns out that they completely dominate the signal that you would see with an interferometer. So on the right is actually the interferometric response, the visibility amplitude that you would see as a function of the baseline length for the image on the left. And on short baselines, you're dominated by the astrophysical emission, this complex emitting material. But once you get to long baselines, you get dominated by the subrings. And these photon subrings have a universal appearance on long baselines where it's just a damped periodic oscillation, where the period actually tells you the diameter of the subring along that baseline direction. So in this case, the blue curve here is for a horizontal baseline, and the red curve is for a vertical baseline. And what's extraordinary here is that you'll see that they have slightly different periods. You can see that the blue peaks are sliding a little bit with respect to the red ones. And the reason for that is because the photon ring is actually compressed in this particular image by about 1%. It's not a perfect circle. And the thing that's doing that is the spin of the black hole. And while this is something that you couldn't hope to read off the image, it's a booming signal in the interferometric domain where you can just read off the black hole spin from these shifting subrings. So as an example of this in the center, it's just showing a perfectly circular black hole shadow that you would see for a non-spinning black hole that's surrounded by a circular photon ring. Then what we can do is we can spin up that black hole. And as we spin it up, it turns out that the black hole shadow gets displaced a little bit, and this bounding critical curve gets compressed. It gets flattened more and more in the horizontal direction as you approach this maximal spin. So it's this extraordinary case where in the beginning, in the creation of the EHT, we were fixated on things like the density of our UV coverage. If we want to double our resolution, we need to fill out a whole array that fills out that UV space, because a single baseline by itself can't tell you very much. But it's this wonderful property of the black hole that's actually giving us a signal that's most natural to probe directly in the interferometric domain. And we don't need a full dense array to do that. We can actually study it using only a single baseline. It's even better than that because baselines, they don't see things that they resolve out. So the subrings actually decouple. Whereas you go to longer and longer baselines, your baselines will progressively resolve out some of the subrings, and it'll see just one at a time. So there's a way that you can look through this cascade of damped oscillations to actually see each subring independently. Whereas on the image, again, it's complicated. They're stacking, whereas in the visibility domain, they natively separate. So the black hole is really giving us this gift. It's a way to study it in an entirely new way. We couldn't do this for any other type of astrophysical object, but it's the strong lensing of the black hole that gives us a pathway to making much sharper resolution images without needing to build out an entire array that's dense at a higher resolution. So before I close, I just want to emphasize that the EHT collaboration consists of more than 300 scientists, more than 60 institutions in 18 countries and regions. this is a big group, and we simply couldn't do the science that we do without many extraordinary contributions, ranging from senior scientists all the way down to even undergraduates in the collaboration. So it's really a privilege to be part of it, and I encourage anyone who's interested in this to reach out, and we're always happy to engage with external teams, and we continue to grow. The EHT has really extended the VLBI technique to the highest frequencies it's ever been done, and this has allowed us to study black hole images directly using VLBI. So our first images of M87 in total intensity revealed black hole shadow, and they allowed us to estimate the mass of the black hole to within an accuracy of about 10%. Just last week, we released the first polarimetric images of M87, and these indicate that the black hole in M87 has dynamically important magnetic fields near it. And we also find that the only models that are consistent with both the polarized images and also producing enough jet power are those where it's strong magnetic fields near a spinning black hole. And we're working hard to continue to improve the array, and we think that a next generation EHT could directly link the dynamics of this black hole to the jet in M87. Could make movies of both M87 and Sagittarius Star, and using these properties of the black hole lensing, we think we could sharpen the resolution by orders of magnitude. So it's really an exciting time for black hole science and for VLBI. And thanks so much for letting me share this with you today.
Thank you very much indeed, Michael. That was a lovely talk, and lots of very interesting thoughts. Now we've got some questions for you. Let me see. A question that relates to the beginning of the talk. Were any of the artifacts on the separate maps made by the different teams, the 4 teams, either along or perpendicular to the M87 jets?
Yes. I'll just point out a few. So the M87 jet is this very narrow feature on large scales, and on small scales, it becomes broader and broader, and it's sort of a parabolic opening. The jet comes off in something like this direction, and so there's a lot of excitement that this feature down here might actually be part of that forward jet, part of the opening there. There are also hints on the opposite side that could be part of the counterjet. This is a place where it's transrelativistic, so you might not expect that you only see just the forward or the counterjet because of the Doppler effect so much. Now, this is something that we don't feel confident in claiming. Other groups are studying this. I think we'll learn more and more. But this is something where certainly the addition of something like the Kitt Peak Telescope or NOEMA, where we get a few more short baselines, this is going to make it absolutely clear whether or not these are the base of the jet or whether they're just imaging artifacts. These are also in a place where the dirty image has a lot of power.
Okay, another question that's a little bit related to that. I would say it's probably fair to think that even though they were isolated from each other, all of the 4 teams probably expected to get something like a ring structure. Did you ever have any concern that this might have biased them in their imaging of the data?
Constant concern. Yes. 2 years of stress dreams and panic. I think we were all, there's a worry that maybe you're leaving something on the table, and we're not pushing our algorithms hard enough. But certainly, all of the discussion for the years that we analyzed these data were the terror of publishing a ring and then learning later that we had misinterpreted that. So in the synthetic data set that we made to train these algorithms, we had things like top hat disks. We wanted these algorithms to work very well at reconstructing things that didn't have a depression in the middle of the ring, or doubles where there's no ring at all. There's no circular morphology or anything. So we tried to build in safeties where we could catch ourselves if we were seeing something that was too similar to what we might expect. But of course, it's something that fundamentally the only way to test this is go out and take more data with a more capable array. And we're confident that these will hold up, but we're of course open to being completely surprised.
Okay, a couple of questions related, I guess, to some of the variability that you've seen. What is the orbital period for material at 50 microarc seconds? And do you have ideas about the physical interpretation of the variability seen over a week?
Yeah, so it's rather interesting. Actually, not sure where. So we see that this ring is bright on the bottom and faint on the top. And we think that that's because of Doppler effects, because the material is circling the black hole. And so it's actually rotating clockwise on this image based on the inclination of the M87 jet. Now, if you look in total intensity, what you find is that on April 5th and 6th, there's a little bit more flux here. And then it moves down to the lower right of these images. So it's actually, if you interpreted this as a coherent rotation of a feature, it's going the wrong direction. It's more likely that these are just random brightening and fading of material as it's orbiting around the black hole. So I think the assumption is that it's stochastic image variability, and that will be borne out by additional observations with finer cadence where maybe you could track things directly. So, I mean, that's roughly the sense of it in terms of the physical interpretation. But of course, again, we need more information to pin that down. And I'm sorry, there was a first half of that question that I think I forgot.
Let's see. I think what was the orbital period for material 50 microseconds? Yeah,
so the gravitational timescale for M87 is something like 9 hours. And so an orbital material, say the ISCO period for a rapidly spinning black hole would be about 4 days and be more like a month for a non-spinning black hole. So we think that this does kind of align with the orbital periods that we would expect for material near a 6.5 billion solar mass black hole.
Okay, we've got a few questions about things that you may or may not be able to measure with the sort of data that you're getting. Can the polarization measurements and imaging say anything about which direction the black hole is rotating?
Yeah, so one thing that we concluded from the total intensity is that in order to produce a jet that's as powerful as the one seen in M87, the black hole has to be spinning. And because we know the orientation of the jet and because the image is bright on the bottom, we think the spin vector is kind of into the page here. So we have a pretty good handle on the direction of the spin because we think that material that's this close to the black hole has its orbital direction set by the spin. We don't, even if you start with a retrograde flow, it will realign and be co-rotating with the black hole spin in this case. Now, we actually have very weak constraints on spin beyond just being able to say that we think the black hole is spinning. And that's something where I think there's a lot of work being done. There's kind of two directions you could go. One is to look at the photon ring, the black hole shadow, and use properties of the lensing to infer properties of the black hole. So that would be an astrophysics independent measurement of the spin. It'd be very powerful, but it's certainly going to require a different array. And the second thing you could do is really do an intense monitoring campaign. And this is something that we're trying to set up for the coming years, where we would actually monitor it not over a week, but actually over months. And this might allow us to see the coherent rotation through a reconstructed movie on these horizon scales. So this is something that there's a lot of algorithmic work needed, but also a lot of work just to make the instrument capable of that type of campaign.
Okay, and another question sort of along those lines. Are there any observables that you can get from VLBI to distinguish charged versus not charged black holes?
Well, we don't think that black holes are charged because we think that they would rapidly discharge. So the constraints are extremely stringent just based on rather simple arguments. Now, you could certainly say, I still think that a charged black hole might be viable. Maybe there's some physics we don't understand. I would say this type of analysis hasn't been done where you're running, say, full GRMHD simulations with a charged black hole. But people have looked at how, say, the shadow of the black hole might be affected. So I actually don't remember offhand how stringent those would be. In the best case, I'm guessing that they would be order unity constraints on charge, so much weaker than something you would get from just first principles arguments. But it's an interesting question, and if there was a well-motivated case to be tested, it'd be really interesting to compare that directly with our data.
Okay, let's see here. What do you think the regime of synchrotron emission is that you're dealing with? Is it optically thin? And it looks like the polarization degree increases with distance from the shadow center. And can you tell whether it depends on the azimuth angle? Or do you not have data for that yet?
That's right. So the dependence on azimuthal angle is certainly pretty reliable, that the polarization occurs dominantly in the southwest. The high polarization at the edges of the image can be artifacts because the intensity is very low there. You're kind of reaching the dynamic range of our images. So the conclusion that the polarization fractions are high there, I think, is not secure. We think it's optically thin for a few reasons. One is that we see the shadow. So if it was completely optically thick and self-absorbed, you might just see a featureless blob on the sky. The spectrum of M87 is fairly flat, and these GRMHD simulations are all really becoming quite optically thin when they're tuned to match the data. So I'd say there are lots of lines of evidence that point to this becoming, it's sort of a transition regime, but it's becoming optically thin. Yeah.
Okay, and another question about the polarization. Regarding the 3 fractional metrics that you showed, which included Stokes Q and U, is EHT actually able to resolve Stokes V for circular polarization in the data? Is that a realistic goal? Yeah,
so Stokes V is what we measure at all telescopes except ALMA with circular feeds. So measurements of Stokes V are really sensitive to calibration assumptions. Mm-hmm. We have algorithms that are able to simultaneously estimate those calibration terms and the Stokes V. So I think there's hope for actually scraping out some results on that, but it's not something that was part of our initial results. So we did release a paper last week led by Chiriaco Gotti, just with ALMA unresolved linear and circular polarization of M87. But I think getting EHT circular polarization images is something that's going to take more work, more algorithms, more validation, and so forth. The prospects are, I think, promising for doing that regularly in the future, especially with more sites and more redundancy for calibration. But it's a challenging problem.
Okay, a very different but very important, I think, question. From its inception in the 1960s, VLBI has been a tool of science diplomacy. The EHT and your work on the M87 black hole have been inspirational and caught the imagination of the world. I think that's a very fair statement. Have you considered making the next generation EHT an inspirational instrument for world capacity building, as well as a facility for pure science, maybe in collaboration with the IAU Office of Astronomy for Development?
So I would say the NG-EHT will only exist if it's a global collaboration, both in terms of funding and in terms of logistics. To operate a global array, there has to be buy-in from all these different regions. Whether this IAU office is something that could be part of that, I don't know. I would love to learn more. But I think the EHT was only successful because of the global coordination and collaboration, and it's something that I think we can only hope to build on for any sort of next generation effort.
Okay, it'd be lovely to see that happen. Let me see here. Okay, a couple of questions about possible future. Are space VLBI projects being considered to detect the photon rings, or could they be detected with Earth-based baselines only? So what about space VLBI and EHT?
Yeah, so a number of space concepts are being pursued. So space VLBI has been demonstrated using a few missions in the past, VSOP in the 90s, and then Radio Astron more recently, which operated from something like 2011 to 2020. Radio Astron in particular had baselines extending to about 300,000 kilometers or 30 Earth diameters, the distance to the moon. So it's an incredible precedent for millimeter VLBI. And the challenge is that the highest frequency of Radio Astron was about 22 gigahertz, where this M87 system is still optically thick. So we want to increase the frequency by about a factor of 10. So we're at the point where I think I saw Leonid Gurevitz on the call, and he'll tell you, and I completely agree, that millimeter space VLBI is it's inevitable. It's going to happen, and it will be routine. Just the question is when. I would say the challenges for doing it in the next decade are fairly formidable. We need to be getting massive amounts of data down from orbits, and we want to be in these distant orbits. So we're trying to downlink, many terabytes or probably petabytes of data, which is a challenge that a decade ago would have been impossible, and now is actually becoming feasible with laser communication. In addition, we need to get sufficiently large dishes in space, and we need frequency standards that are reliable enough for these high frequencies. So there's a lot of different mission concepts planned, everything from low Earth orbits to something like L2, 1.5 million kilometers. And for these photon ring studies, these extremely long baselines would be incredibly effective if we can get the sensitivity sharp enough that we'd be able to make measurements.
Okay, and what about the possibility of detecting merging events with EHT? I think something, maybe binary systems merging inside the accretion disk, or objects falling onto the central black hole. Is that something that's of interest and feasible?
Definitely. Feasibility. So one of, I said our first image was of M87, but we actually observed many targets, not all on horizon scales. So one target that we've observed almost every year over the last decade is OJ287. So this is this putative supermassive black hole binary system. And we also observe regularly 3C73, which has maybe some hints of being a binary. So I think it's unlikely that we would see mergers of supermassive black hole binaries. The timescales are just too long, but it's certainly not impossible that we would get lucky and we might have the same source that maybe a pulsar timing array could detect, that we could also resolve the separation. So there's, of course, this famous last parsec problem. How do supermassive black hole binaries merge in the final parsec, where they're a bit too far apart for gravitational waves to kick in. And the EHT could resolve the final parsec of separation over all of cosmic history. So I think it's a really exciting prospect for these next generation concepts as we push to more sensitive arrays to see if we can study supermassive black hole binaries. Now, in terms of accretion events like tidal disruptions, I think we would have to be pretty lucky to be able to detect an event. And even if we did, the separation that we can resolve is quite large. So I would say I don't know of any immediate prospects for observing events like that, but we could certainly just be watching Sagittarius star in real time. And to put it in context, a day in the life of M87 is a minute in the life of Sagittarius star. So this is a source where if we could build out an array, we could just build a monitoring campaign and be watching black hole accretion, see daily flares, and see how material behaves right near the horizon.
Okay, thank you very much. I think we probably need to stop there. We've got a few more questions that have come in, but most of them have been answered. Thank you very much to Michael for his very informative and interesting talk. And thank you very much to everybody who came and everybody who asked questions. All the best.
Thanks all.
It's a actually it's a lovely way to ask the questions because you get to see them all. You can like try to group things together and you try to put some order